Lego Boost was released in 2017 as Robotics and Coding Kit for Children. It was later discontinued in 2020. After that, Lego shifted its focus to newer robotics platforms, and the successor to Lego Boost is Lego Spike today. So Lego Spike, such as Spike Prime and Spike Essential, is the main educational robotics system used instead of Lego Boost. Lego Spike doesn't have native AI support. Both Lego Spike Prime and Lego Spike Essential do not include built-in artificial intelligence features such as machine learning, vision AI, or any kind of intelligent assistant. Instead, they focus on traditional robotics programming using block-based coding and Python, where behavior is controlled through rules, conditions, and sensor input. For Lego Boost, it requires a tablet or compatible device connected via Bluetooth in order to run and control the models. Pybrick is an open source robotics platform that lets you program Lego smart hubs using Python, the MicroPython, and block-based coding. It allows you to run programs directly on the Lego hub itself, instead of relying on a tablet or phone during execution. So it's possible to use tools like Pybrick to replace the original firmware on Lego Boost and run custom programs directly on the hub. In that case, the robot can execute programs autonomously without needing a tablet connected via Bluetooth during runtime. To install the Pybricks firmware, we go to codepybricks.com, open the Tools menu, and click on Install Pybricks firmware. Then follow the on-screen instruction to select your hub and complete the instruction process. And next, so just follow the instruction. So note that later you can also restore the official Lego firmware. Firmware has been successfully installed. Inside this code pybricks.com, you can create a Python file and choose whether you want to use code blocks or code with Python. Let's select code blocks this time and name the file, say test Lego. When you create the file, we see setup and program blocks. Note that we can click show code to view the code, but in the code blocks option it's read only, so you cannot type anything here. From the setup, I drag this motor 2 times and rename to left and right. And for motor left, I change the direction to counterclockwise, which I'll explain later. Then I add DriveBase and map left to left and right to right. So we'll discuss these two parameters, 56 and 114, later. As you can see, these setup blocks are basically important object creation like motor, DriveBase in Python. So when you right click and click help, so when you right click and click help, you get documentation about that block. For example, I clicked on DriveBase and read about it and its properties. So using DriveBase is better because it combines two motors into one control system, so you don't have to manually coordinate each motor. Instead of writing separate commands for the left and right motors, the DriveBase lets you control the robot like a single unit. You can move forward, backward, turn, and stop with simple commands. It also handles things like straight line movement and turning more accurately by synchronizing both motors internally. So without DriveBase, you would need to constantly calculate and match motor speed yourself, which is harder and less precise. From the output, I drag the DriveBase DriveBase block. So this is the program section. So it means the robot will drive straight forward for a distance of 200 millimeters using the DriveBase. The hub integrated drive system consists of a left side motor, it's motor A, and the right side motor, it's motor B, supplemented with one external motor and two interface ports. We will use the external motor and two interface ports when integrating it with AI. I have two wheels and I will connect them to motor A and motor B. For the drive base, we have, you see we have the diameter of the wheels and the axle track. which is the distance between the points where both wheels touch the ground. Let's measure the diameter of our wheel. It's about 30 millimeters. We change it to 30. And the measure the Excel track. It's 65 millimeters. Change it to 65. Read the wheel diameter on the Excel track because the DriveBase uses them to understand how your robot moves in real life. The wheel diameter tells the system how far the robot travels when the wheels rotate. Bigger wheels mean more distance per rotation, and smaller wheels mean less. The axle track is the distance between the two wheels. It's important for turning because the robot needs to know how wide it is to calculate how much each wheel must rotate when it turns. Without these two values, the robot would not be able to move accurately. It would either overshoot distances or turn incorrectly. However, the movement will not be perfectly precise in real life. Factors like friction, wheel material, and the type of floor can affect the accuracy, so the robot may not always move or turn exactly as calculated. When we observe the motor hub moving forward from the left side, moving forward, the wheel connected to port B rotates clockwise. However, however, for motor A move the same forward direction, its wheel must rotate counterclockwise. So we already specified it in the setup already. Now we can test the robot. First, we have to connect it via Bluetooth and then run it. I have a ruler set to 200 millimeters. Let's see if it moves 200 millimeters with the wheel diameter we specified. Yes, it moved 200 millimeters. Once you deploy the code to the hub, the program is stored on the hub itself, so you can then disconnect from the computer or tablet and run the program directly from the hub, allowing you to take the robot anywhere and run it without maintaining Bluetooth connection. So I'm disconnecting the hub from the computer to test it. Yes, it works. With Lego Boost, you can create a more advanced robot that performs interesting tasks. In this demo, I will showcase features that use both port interfaces and an external motor to better demonstrate AI functionality. Now let's build a Lego model that uses both an external motor and two interface ports. The first piece I, I built uses external motor, and on the top of it it's a rotating cylinder with four color panels. The second piece is color sensor, which is directed towards the colored panels. So it detects and identifies the color in front of it. Note that the Lego Boost color sensor is a combined multifunction sensor that can detect colors, measure light intensity, and sense nearby objects. Once the robot identifies a color, it will move in different directions, drive at different speeds, and make turns at different angles based on the detected color. A user can enter a prompt in the app to define how the robot should respond to each color, such as stopping, moving backward, increasing the motor's rotation speed, or performing other actions. And the third block is the back wheel. It has no motor and rotates freely, following the direction of the front wheels. Once I have these blocks, I can assemble them together using the Move Hub. So I will connect the motor to port D and, and the color sensor to port C. So let's do it. So here is the final model. As we built our model, the robot, we can create code for it. Previously, we created our test Lego code using Pybricks with block-based programming. But this time, we are implementing it using Python. I already created the initial version of the robot code in Python for our model. As you can see, there are no blocks anymore, only code. Since we are going to integrate AI, it may be better to use a full-featured IDE to generate the project code, including the robot logic. For that, I used Cursor IDE, and the project you see was generated entirely using prompts, including the robot code. When we say entirely with prompts, it doesn't mean the system magically produces the final project that you can simply run. You still need to define what and how to build the project, review the results, and iterate until it matches your expectations. Prompt-based programming doesn't remove the need to understand Python or Lego systems. Let's look. Let's take a look at the robot code. So we use strategy pattern in the robot code. It defines a family of algorithms, encapsulates each one in a separate class, and makes them interchangeable at runtime. Note that the Lego system has very limited memory and storage, about 64 kilobytes of RAM and up to 1 megabyte of flash storage. If we use too many classes or objects, we may exceed the available memory. Strategy-based class color strategy. This defines a common interface, and each strategy must execute. Strategy implementation. Drive strategy. This is one specific behavior. Drive with speed and turn rate. Strategies is here we map each color to a different strategy. So color green is fast driving straight. Yellow is turn. Blue is turn in the opposite direction. And red is stop. The strategy pattern allows the robot to choose different behaviors at runtime based on detected color without changing the core control logic. The system initialized a motor on port D and color distance sensor on port C, then starts the motor using the configured speed value. The hublets are used to visually indicate the robot state or detect its sensor values by turning the move up light on, off, or changing its color. When the application runs, it uses default settings. Instead of hard-coding exact colors and speed, we can also use higher-level prompts to generate different robot behaviors. Let's test our robot first without AI. First, you have to create a virtual environment and install the required packages. To do that, we run the setup command. It will create a virtual environment and install all the required packages. This is our robot code. We have 115 100 millimeters per second movement, 90-degree rotations, and for motor 25 degrees per second. We will debug the application later. For now, we run the hostpad command to start it. So you can turn on the move up before running the command by clicking the green rectangle button on the move up. On connect you see the initial missions parameters being uploaded, the default speeds and turn rates for each color, plus the team motor speed. We are deploying the mission to the move hub. The toggle voice the transfer state. You can see that when sensor detects green, the robot will move forward. For yellow and blue, it will turn 90 degrees in opposite directions. For it will stop when the sensor doesn't detect any color while the motor is rotating and there is no color in front of it, the robot will stop. You can also see the hub blades matching the current power. Let's take a closer look at the robot. First, note that I will not run the application using hostpath because I have already deployed it to the Move Hub and I can run it by just clicking the green button. What I want to show is how DriveBase helps with both movement and especially turning. We specified, we specified a wheel diameter and the axle track for 60 millimeters. Using these values, DriveBase automatically calculates how much each wheel should rotate to move a given distance or turn by a specific angle. So for green, for this green, the robot moves forward and you can see that both wheels rotate at the same speed. For yellow and blue, the wheels rotate at different speed. The wheels rotate at different speeds and in different directions, allowing the robot to make 90-degree turn. DriveBase performs all of these calculations for us, making our lives much easier. As I mentioned earlier, the terms will not be perfectly accurate in the real life. Factors such as friction, the wheel material, the type of floor, and even battery level can affect the accuracy. Let's run it. Now that we understand how the robot works and the parameters it uses, we will use AI and high-level prompts to change the robot's behavior. When we run the robot, it starts automatically with the current parameters, and we are also provided with an input where we can enter a prompt to modify its behavior. Sometimes we want the robot to wait until we provide a prompt instead of starting immediately. In that case, we can enter S, stop, and the robot will stop and wait for our prompt. We will see this in the debug section. Once the AI generates new parameters based on the prompt, the robot code is updated and deployed to the Move Hub with those parameters. For the AI, we use OpenAI's ChatGPT for our mini model to interpret the prompt and generate the appropriate parameter values. So let's start the application. I'm typing S to stop, and the robot has stopped. My prompt all counts will be 0 for red and green. The robot moves forward at speed 50. And for the other colors, it moves backward at the same speed. The motor speed is 15. You can see that the code is generated with those values and deployed, as you can also see in the console. Now it's moving forward and backward with the opposite colors going forward while the others go backward. The motor speed is lower than before. As the rear wheel depends on the front wheels, so the backward and forward movement will not follow perfectly straight line. Now, when I run another prompt, only the parameters mentioned in the prompt will change, and the rest will keep their previous values instead of going back to defaults. This time I don't type based on I'm typing. Make the motor speed You can see that the previous parameters are still applied. Terms are 0 and the speed isn't changed, but the motor speed is higher. Now, as the motor speed is higher, the robot switches between forward and backward more frequently. I'm typing S and say only yellow moves at speed 50 and turns minus 25 degrees. The other colors do not move. Only yellow moves at speed 50, turns 90 degrees. Do not move. So it's changed. When we start the application via host path, this main passes two arguments to run host. It's the hub name, the Pybricks hub, and the args timeout. This scan timeout time, scan timeout. So find device scans over Bluetooth for Pybricks hub, matching hub name, and returns the device if found within timeout seconds. Pybricks hub Bluetooth device grabs the Bluetooth device from find device in Pybricks app client so the app can connect, upload programs, and read app output over Bluetooth. This Hub Connect opens Bluetooth connection to the hub so the host can send programs and receive data from it. This mission state holds the live mission settings, speeds, turn rates, motor speeds, and keeps them in sync safely while the hub sends updates. So current parameters, their current mission, its current mission values start from defaults. Log prevents race conditions when params are read or updated at the same time. Apply result updates current params from hub result message. And snapshot returns copy of the current params for the AI prompts for upload. This run mission deploys a new mission to the hub in order. Like clean up, stop, the old program, generate the script, upload, then listen for hub feedbacks. So await stop reader, cancel the background task that was reading hub output from the previous run, so two readers don't run at once and all the result lines don't update state after redeploy. Stop user program stops whatever program is currently running on the hub before uploading a new one. This prepare mission control copies template mission control Python into generated folder, injects parameters like speed, turn rate, motor speed into host params block. And returns the file path to upload. This hub run uploads and starts the generated script on the hub. Returns without waiting for the program to finish. This create task starts background task that reads hub lines, parse result, messages and updates, mission state, current parameters, so the next AI prompt uses the hub's latest values. We already debugged the application with the default parameters. Now let's prompt and debug it. I will type turn all turns to 0, but first I'll type S to stop the application. So after the prompt, it will call handle prompt. So I'm typing turn all turns to 0. So first we get the current parameters from state snapshot. Then we call parse mission prompt in host AI. So parse mission prompt in host AI is synchronous. It calls the OpenAI API and blocks until the response arrives, wrapping it into async to thread, runs it in a worker thread so the async event loop, Bluetooth hub, input output, background reader, etc. is not blocked. So we pass so we pass in what we typed plus the current parameters. So it calls GPT and returns structured response instead of loose text. So Pydantic defines that shape. So mission params represents the nine integers, speeds, turn rates, motor D, and the mission input wraps them with changed, which parameters were modified, and the reply what to print. These classes are both Python types and the schema for OpenAI structured output by completions parse. So you get real mission input in message parse, no manual JSON parsing. After that, the model after the model responds, the validated params checks the values that the turn rates are limited to plus minus 360 and everything else to plus minus 500. Then model dump converts it into dictionary to deploy. As you can see, in run mission, all the new parameters, all the turns are converted to 0, are turned to 0. So we can see that mission control PY has the updated parameters under generated. All turn values are now set to 0, while the template remains unchanged.